So it was a continuation of the statistics review. We ended off together. We talked about different kinds of, we talked about the standard deviation in detail because I explained that statistics is about averages and relative measures and nothing better than the standard deviation to show those, both of those themes, right? So you have the standard deviation, which is the square root of the variance. The variance is the average of the squared deviations from the mean, measuring how spread out data is. Okay. And then together we solved that, and then we solved this one. I showed you how to do this in Excel. And I did this because you're going to see this a lot. Okay, so you have data that is historical. It's every observation has an equal significance or value. So your average is just a regular average, and your standard deviation is a regular standard deviation. But when the data are presented like this is representative of a population. We use symbols that reflect parameters, mu and sigma, for mean and standard deviation. And I demonstrated how to calculate that with Excel. So I expect you to know how to do that. That's what we did before the weekend. And then I asked you to watch some videos that did some more statistics. In particular, you reviewed or you were introduced to scatter plots. And I pursued a discussion about looking at two variables at a time. And looking at two variables at a time, we look for a linear relationship or trend between those variables. And I talked about the correlation, the measure of the correlation coefficient. So if you didn't have a chance to watch those videos, please do. I talked about the correlation coefficient being between -1 and +1 and what you would expect. A perfect positive relationship would look like this, and it would be, R would be +1. A perfect negative relationship would look like this. So R is a measure of the direction and strength of the linear relationship between two quantitative variables. So direction is seen by if it's positive or negative, and strength is how close it fits to the line. So the stronger it is, the closer it is to 1. The stronger it is in the positive direction is closer to +1, and then in the negative direction close to -1. When there's more scatter, it's closer or moves towards 0. The worse it is in scatter, away from the line, it's even closer to 0. This is an example of no relationship, where you could see, if anything, I put a flat line across this data, indicating a no trend. And then I differentiated that between an R of 0 with no relationship to this sort of relationship. It's not a linear relationship, but it's a curved relationship. It's still a relationship. And I suggested you shouldn't calculate R for this because it will be misleading. And then I spent some time on some examples using financial data. So then I bring it together, the statistics tools that you should have learned, together with some finance application. So I did that with these two sets of data. This is the data as historical, so every observation is equally likely, and thank you. Every observation is equally likely, and so we calculate this like this regular sample mean and the regular standard deviation, sample standard deviation, and then I talk about this is the covariance. If you remember, it looks like the variance, but I'm correlating X and Y. And then I explained what is correlation. It's just the standardized covariance. It returns, or it turns, this value, which for different variables it's not exactly meaningful what a covariance is giving you, because they have a different kind of spread. So the data could be, a variable x and a variable y, that you don't really understand the range of values or their covariance as a measure. So by standardizing, dividing by the two standard deviations, you convert it into an index that you can interpret, because the index is between -1 and a 1. And then I just wrote it a couple of different ways, but these are all the same, essentially. Writing it this way is nice because it shows you that all we're doing is standardizing the values, or standardizing the values and converting this into an average of this multiple that becomes positive if the trend is the same with x as y, and if it's opposite, the trend will be negative because of this multiplication. So multiplying a positive and a positive gives you a positive r if that happens repeatedly, and if when x is below its trend, y is above the trend, you have a negative relationship. Or sorry, when x is above its mean, y is below its mean, so they behave differently, then you would have a negative, because you'd have a positive times a negative, and contributing negatives to the r. So that's how, this is the variation of the formula that we focus on, really. The most. And then I talked about calculating the slope and what it means. So is everybody okay with this data? Please tell me yes or no. And these results and the interpretation. Do you say it's okay, so you want to keep reviewing? Well, you need to really understand this as this, so basically what do you see here in the relationship here? How are those two variables related? I'm going to have to tell you to watch the videos because I can't go back. We don't have time. So make sure you watch. I put them in the description. I know that I linked them. I mentioned them. I guess I could give the links too. All right. So then this relationship is replicated here. Not replicated, but this relationship is explored between these variables, but I presented them in a different way as ex-ante data, where they become like a distribution. It's a discrete distribution. It tells you the different states of the world, what can happen. And the chance of it happening, the most likely in this analysis, is the normal state. And this was determined by using historical data, some information about expectations, some economic forecasts, and these numbers were derived. And then I say to you, well, you're going to do the same thing, but you're going to use the formulas, for the more general formulas, the formula for the weighted mean, the weighted standard deviation. As a result, you get the symbol mu because these are distributions. So this is the weighted mean, the weighted standard deviation, the weighted covariance, the weighted correlation. So again, this is the form of it that you're going to get more used to in this class. And this is the weighted beta. So anyway, watch those videos because I don't want to go back. I'm just recapping what you need. You really need to understand that well. I don't want to say too much because then you're going to think I explained it, and I didn't, because there's much to see in there. And then what I do is I give you the answers to solving for those, so you can check your work. Now in this one, you see that the relationship between them is double. When x is something, BCE is double. So what does that mean? If I was going to make a linear, if I was going to display a scatter plot of this data, I always make the market, in finance, we always make the market X and the stock Y, okay? Because what we're trying to say is the market influences Y. And we have historical evidence for that, so we're relying on theory to be able to do that, right? Not just some data that we pulled out and we correlated. There's actually some rationale for what we're doing. So we put, otherwise, you shouldn't just say, oh, look at this trend, these data are correlated and one causes the other. But in this case, because of the theory, we use X as the market. This is a measure of the strength of the economy, economic performance. And we always put the stock here. And you see a duplication. So how does that reflect here? It turns out that this is a perfectly positive relationship in terms of correlation. And the fact that it's double reflects in the slope of this line. B will be 2. And I explain that to calculate the slope, we use the results of calculus that tell us when we optimize, we're saying we want the line that fits closest to all of the points. We are going to minimize the residual of being off that line. So we calculate the least squares minimum. So we minimize the sum of the squared residuals. And so that calculus results in this formula. So I go through explaining where that comes from, or reminding you, because you should have seen this before, and I refer to the mnemonic device to remember that as risk. So it's R SY over SX. You got to remember the general pattern, but it's SY on top and SX on the bottom. And why risk? Because B, the slope, is a measure of the sensitivity of the stock returns to the market. When the market, based on the market performance, BCE performs 2 times as well. But what if the market performed poorly? If this relationship holds true beyond the range of values of the data, then when the market does poorly, BC does 2 times worse. And that is why we say, it's sensitive, and remembering that it can be good, it can be bad. Doing something like this, though, outside of the range of data is not recommended. It's referred to as an extrapolation, and you shouldn't do it unless you have just reason to do it. But my point is that's the sensitivity. Like it's showing it can be a good thing, it can be a bad thing. But the worst case is, well, it's always doing better than the market. So it means that this can improve your return. And investing in BC. All right, so there's not a lot of you here, but so watch those videos so you understand better what I'm talking about. So I make all the calculations, but in the end, the result is going to be this, and you can see it right away. So it turns out that the line, which I'm not so focused on, but the relationship would be a line that looks like this, and it should be, in statistics we use the prediction line with a hat on it rather than the line in mathematics, because this line should only be used in the range of the data. It shouldn't be used outside. So I put the hat on there to signify that. It's a statistical line, estimation line, prediction line. And then what I do is I have the solutions for the ex-ante data, which you should look at. And you should be comfortable with those formula. And solve all of these. You couldn't. So what I've done here is, you can do this manually. If you just stick with the columns, I tried to line up these columns, but it doesn't look so good. So here, if I want to calculate the variance, it's the deviation from the mean squared. So I just take this column minus the mean, this one, all the way down, and then take this column and put it here. So you're kind of replicating what Excel does, but manually if you were to write this on paper. And so use that concept of Excel to help you organize your paper, your solutions. It turns out that even though you can't see it directly because it's hard to visualize this with probability, it turns out that R is equal to 1 here as well, and B is equal to 2. So you go through the process to verify these. And I have all the solutions there. All right. So make sure you review that. Then what I did was I put on one page all the formula again, using finance notation like your textbook or a finance book would. So these are all the same formulas, but rather than X, I'm putting R for return, return, return. And then what I do next with the notes is get into talking about where R comes from. How did these R's get derived? So it looks really long and really intimidating, but in fact, this is exactly the other formula. So I like to present the other formulas first to make you see that you've seen this before. I'm just making a finance application using a variable known as returns, but the same formula. I do that for historical data and I do that for ex ante data. So do I ever need to see these formula? I don't expect you to rewrite these formulas at all, but you should be able to read them and confident what you're looking at, knowing that this is the weighted standard deviation, weighted covariance, and this is the weighted correlation. You should feel all right about seeing that. So notice I'm going to go through this a little bit before I continue. So if I continue with the convention of putting the variable here for the market, I'm going to end up calling that now M as opposed to X, right? So this is RM, the market returns. And then here I'm going to put Y will be for the variable, the stock return or the company. And we use a notation I for that. So I for the stock is on Y, and M for the market is always on X. That's important for the notation, to feel comfortable with the notation. If I was to calculate correlation, so correlation with the sample result, so this is the formula for the setting of historical data. But now let's make a translation. Let's go from the correlation for historical data. Now let's do it for ex ante. For ex ante, I would write it as, I'm going to use the Greek letters, and this would be covariance. Are you with me? I don't know why I can't erase that. And then this would be the standard deviation of each of those. How's that? Comments? So this is historical data or ex post. This is for ex ante. And then I want to do it for, I have to put, it's like that. That's the symbol that I used. Let me see what I did. Go back a bit. 6. I have to go back to the formula over here. So these are the symbols that I used for correlation. It's a Greek letter R for regression. So this is for ex post, this is for ex ante, and how would it look for finance data would be, or I could write this as xy here as well, because it's the correlation between x and y. So for my case, it's going to be, I guess I'd put in alphabetical order. So, and it doesn't matter if x comes first or y comes first when calculating the correlation. Remember that, because the formula does the same thing to x as it does to y. If you just look at this form of the formula, whatever you do to x, you're doing to y the same. So it doesn't matter if I put y first or x first, but it's a tendency in statistics to put things in alphabetical order, so that's why x comes first and y. So when it comes to when x and y are m and I put the I first, im. And then this the covariance would look like im, and the two standard deviations would be sigma I, sigma m. So this is for finance notation. Okay, so I'm just doing the translation. This is like Google Translate. Now I've done that for correlation. Let's do the same thing for the betas. I'll do it in the next column beside it. So for beta, or b, the slope, it's r sy over sx for x post. For the slope, we use the beta symbol because it's Greek letters. We're treating it like it's a distribution and represents the population. So this is beta, this is rho, and then sigma y over sigma x. And I could put xy in there too, but I don't because it's obvious. And just to be fancy, however I do it here. So the beta of im for finance the beta is also r sy over sx. In finance, the rho is, or the correlation is rho im, and then I have to put the y variable on the top, so that's I, so sigma I divided by the x variable, the horizontal one, in the denominator, so that's sigma m. So I just did a translation of the several documents. This is what I want you to arrive at, that you end up here. I could also write correlation, or I could also write beta differently because of correlation. If I substitute this expression into correlation, I can get a second formula for beta. So I'm going to substitute this in. And you'll see this will give sigma x y, so the covariance, sigma y, I'm just recopying this thing, but then sigma x, sigma y. So these two cancel, and you have an expression that says that the beta, the slope, is the covariance per unit of variance. That's what the beta or the slope is picking up. The covariance per unit of variance. And finally, that would be here as well. I mean, I'm not going to do it up here, but you could do it for the ex post scenario as well. This is going to be plugging this in, sigma im. Again, these cancel, so it's the covariance per unit, the covariance per unit of variance in the market returns. So, I have the feeling you didn't watch the videos because most of you left and you think you need to watch it, but I pretty much said what the most important things were. But if you feel comfortable, you know, you want to watch those again or you want to watch those, that's fine with me. But we cannot delay, we must move on. So you have all the formulas, they're all there, they're all analogous to one another. So I'm just repeating the same thing with a different data set, different type of data set.